what are the types of errors you can get?
Zero error.
Good, zero error. What kind of error is there still?
Parallax.
Parallax error. Any more?
Got more.
Got
Um,
At least one more lah. At least one more.
human error.
Okay, human reaction time, right? Okay, so I can just put as human reaction time. So these are actually not exactly the errors. These are examples of the errors. Let's write down what these errors are actually. So for zero error and parallax error, they fall into this category which we call systematic error. Heard of this?
No.
Oh no. Okay. Human reaction time falls into this category called random error. Okay. So let's expand on this idea a little bit. What is a systematic error? What is a random error? Okay, a systematic error is when it is a consistent bias. Okay, consistent bias. In other words, you're consistently wrong lah. Yeah. Okay, so there's some usefulness to this. Okay, I'll give you an example. Okay, if you maybe have like a weighing scale in the kitchen or something, and this weighing scale is a bit sort on, right? So every time you weigh nothing, it is already 2 grams. Okay, so you know that whatever you put, the actual mass is just minus 2 grams. You get what I mean? So it gives you a wrong reading every single time. But I mean, in the end, it's not going to matter much because it's always the same wrong reading. So you can just minus it off yourself. Okay, or like a clock or something. The clock is always 5 minutes fast. Then you always minus it yourself lah. So is the clock accurate? Never. It is never accurate. But you can still get an accurate time because it's consistently wrong in that sense. Okay, so it's not the worst thing. Okay, because in this case, it's called a consistent bias. Okay, what about a random error? This is the one that's actually not very good. Okay, this is actually an unpredictable bias. Okay, because it's unpredictable, you really don't know what the accurate value is. So human reaction time is one that is unpredictable, right? Sometimes you overshoot, sometimes you undershoot. So it's like, oh, so like this time you are doing this experiment, what's the actual value? Actually, nobody knows. Right? Maybe a bit more, maybe a bit less. Okay, so sometimes consistent bias is a bit better for us. So what's the solution? Okay, solution to this is just to minus. Okay, take away the bias. Right, if you have extra time, take away the time. If you have not enough time, right, then you add in the time. Right, say for example a clock. If the clock is running early, then or running late, then you just adjust it yourself. This is quite easy. For a random error, how do we fix this? We fix this with averaging. However, there's 2 ways of averaging, which is not often discussed, and the 2 ways will give you very different results. So a simple experiment that we have averaging for is the pendulum swing experiment, right? The thing that swing, then tell you to record 20 times that one. Yeah. So not sure why we still study that because clearly nobody uses one, right? But it's inside the syllabus. Okay, so we are going to do averaging. Okay, there's 2 ways to do the averaging. This is the first way. Okay. This one you don't need to copy first. This one you can just observe. Okay, so first way is this. You're going to record 20 individual readings. Okay, and then you average the readings. Okay, this is the first way to do it. The second way to do it is you record basically the same thing, right? Similar sounding. 20 readings in one sitting. Okay, and then you average the readings as well. They sound very, very, very similar. What's the difference between the two? The first one is you take a piece of paper, you put 20 rows. Okay, every time it completes one cycle, you write down one number. So you start, stop, then you write down. Then you start, stop again, write down. Then you have 20 of these readings. After that, you add everything up, divide by 20. Can see?
Yeah.
This is the first way. Second way is you start, let this run. After 20 cycles, you stop. Divide this by 20. Can see? Okay, so that's the difference. Which one is better? This one is actually far better. Okay, why? The first one that you're doing, right, Every time you start and stop, every time you do that, you are introducing what? You are introducing human reaction time.
Oh.
Can see, right? So every reading has a bit of uncertainty before, has a bit of uncertainty after. Every one of it has it. So when you're doing an average, right, what are you doing? The true reading in the middle is the same, right? The time for the pendulum to swing is going to be the same. So when you're averaging, you're actually just averaging your errors. Sometimes you're a bit faster, sometimes you're a bit slower. So you're just averaging this part of it. Can see? What about the other one, where you let it run for 20? At the start, you still have the error. At the end, you still have your error. But when you average it, you're distributing this across all the 20 readings. So now each of them contains a tiny slice of error, instead of each of them contain a full error averaged out for 20 times. You can kind of see a difference, right? Okay, so this tells us that this method is not that good, because what you're actually averaging is the human reaction time. So because you're taking 20 individual readings, you can say that there'll be 20 or rather 40 times of human reaction time error. So therefore this is not as good. Whereas this, right, there's only 2 human reaction time errors, because one at the start, one at the end. So this is much better. Okay, yeah, so I guess if you want, then you can put down the second one. This is how you're supposed to do it. But know that this is commonly like phrased in and it's not right. Okay, can you see a difference? Huh?